Oops. Okay, so this is problem 1A. Okay, so this is kind of like cool table that I was mentioning. So here, we know that our starting node is actually S because you see the starting distance is immediately 0, right? So what it means is from infinity, like because this is our starting node, so we will mark that as 0. So it doesn't have any predecessor, right? Because that's the start node. And now we can see there's T and Y, and we're going to update them. So 6, 7. So always ask, oh, is 6 less than infinity? Is 7 less than infinity? Yes, then let's update the predecessors, right? So for T, the 6 was less than infinity, so S, and 7 was less than infinity, so let's update Y's predecessor to S. And this kind of thing keep happening until we process everything, right? So you can see that now, what is the smallest? I think this is there's a priority queue, right? So what we're going to do next is actually we're going to process 6. Think there's a priority queue that kind of have a distance and vertex relationship. And then now, because 6 was the smallest that's in the table in our priority queue, so you can pop that out. And so now 6, and then you kind of see that this is a situation that I've talked about before. So unlike BFS, we actually need to see if this is a shortest path to Y or this is a shortest path to Y. Imagine it could be 1 to S to 2, it could be 1, and T to Y, the distance could be 2. Then which will result in only 3. Then it's definitely less than 7. So in that case, you need to update this, right? But in this specific example, you do not need to update, right? So, but then instead of updating Y, we need to update other. We still need to update other neighbors, right? So we have a pointer to Z and X. So we have updating accordingly. And one thing to note is really important is that you must add the all like total distance you see from the Z is not just 4, it's actually 6 plus 4. And it actually logically makes sense. That is because we need to kind of look at the kind of comprehensive shortest path, right? So which means that every like a node we're at, we should be able to have its distant from its starting node. That's the whole point of going back to the definition. That is what this definition really meant, right? So to every other node, right? So here, that's why we are keep updating this informations. Anyway, going back to Z. So we updated T and then X to T. So that looks great. Yeah. And then now you can ask, okay, what do I need to explore next? Actually 7, right? Because that is the smallest item that we have. And then here we have another link to Z to X, right? So what would happen is we're trying to update both of them and see what happens. So actually X got updated to 10 because from X, so 7 to 3 was actually 10, right? So then it is actually less than 11, so we will update and its predecessor. And one easiest way to keep track of its distance is you don't like, I mean, as a human, without table, we might need to like, kind of like keep it in our head, but we don't really need that because our predecessor will always remember the distance before me. So all I need to do is get the predecessor distance plus the distance where I am currently at. And that's what our pseudocode was demonstrating as well. So, okay, this is 10, and then we're going to do Z. Sorry. So here the T wasn't updated because 7 plus 9 is more than is greater than 10, so we don't need to do that. Okay, so here from X2, so now we know that 7 has been marked, and then you can think about this as being marked whenever you pop from priority queue. So now we need to process X that has distance of 10, and X this has an edge to T, which we already have seen before. The question is, can we update this or not? Nothing to update, right? Because the distance from, we can see the Y, Y was 7 plus 2, it's 9, right? Whereas this was actually 6 only getting from this one straight edge. Now, you see, so this Z really doesn't have much impact on our currently like finding a shortest path, but we still need to explore because we might like, as a human, we see this graph, but how really these graphs are often represented are just a simple maps. So we really don't know until we traverse everything, until we process everything. So then here we will process C, and then now everything's our process. Okay, so that's And then one thing to mention is that now we get this SPT, right? Shortest path tree. That's what you get on the weighted graph by using Dijkstra's algorithm. And remember that the shortest path tree, the definition of tree is always the number of vertices minus 1, right? Because the vertices are 2 vertices, but there should be only 1 edge between them. So that was really what definition of tree